Bismillahirrahmanirrahim. In our last class, we had discussed about the divergence of a vector field. We can define the divergence of any vector field as the total outward flux that is leaving any volume element enclosed by a closed surface per unit volume as the volume shrinks to zero. So this is actually the divergence of any vector field. Today we will discuss about the Maxwell's first equation. As we know that divergence of an electric flux density is defined as the closed surface integral of the electric flux density per unit volume as the volume shrinks to zero. Or we can also define the divergence of a vector field D as the total outward flux that is leaving a differential volume enclosed by the closed surface per unit volume as the volume shrinks to zero. This is actually the definition of the divergence. So the first equation is actually the definition of divergence. Now when we apply this definition to a differential volume element in Cartesian coordinate system, we will get the second equation. If we apply the definition of divergence to a differential volume element, we will get the second equation, which is actually the divergence of a vector field D is equal to partial by partial x of dx plus partial by partial y of dy plus partial by partial z of dz. So here actually we have taken three partial derivatives in Cartesian coordinate system. This equation is actually different in cylindrical and spherical coordinate systems, which we will discuss later. Whereas the third equation actually says that the divergence of a vector field D is equal to the volume charge density. If we look at the third equation, this third equation is actually called the Maxwell's first equation. This third equation is actually called the Maxwell's first equation. Now how can we derive this Maxwell's first equation? We can derive this equation from the Gauss's law. So let's derive the Maxwell's first equation. According to Gauss's law, the closed surface integral of any vector field A will be equal to the total charge enclosed. This is actually the Gauss's law. Or we can also say that the Gauss's law actually relates the total flux that is leaving a closed surface to the charge enclosed by the closed surface. This is actually the total flux that is leaving a closed surface. If A is replaced by the electric flux density, so the closed surface integral of the electric flux density is actually the total flux, the total electric flux that is leaving a closed surface. And Gauss's law relates that flux to the charge enclosed by the closed surface. So according to Gauss's law, the closed surface integral of the electric flux density or the total flux that is leaving a closed surface will be equal to the total charge enclosed by the closed surface. This is actually Gauss's law. Now if we take this equation as per unit volume, it means that if we divide both sides of this equation per unit volume, so the equation will become this, and as the volume shrinks to zero, so the closed surface integral of any vector field A per unit volume as the volume shrinks to zero is actually the definition of divergence. Whereas the charge per unit volume as the volume shrinks to zero is actually the volume charge density. So we derived the Maxwell's first equation from the Gauss's law. Let me repeat it again. According to Gauss's law, the flux that is leaving a closed surface will be equal to the charge enclosed by the closed surface. If we take this equation as per unit volume, so we will get the second equation, and as the volume shrinks to zero, so we will get the third equation. Now the left hand side is actually the definition of the divergence, and the right hand side is actually the volume charge density. So at the end we get the Maxwell's first equation. The Maxwell's first equation states that the flux that is leaving a closed surface will be equal to the volume charge density here. It means that if we have a differential volume that is enclosed by a closed surface, so the total flux that is leaving that differential volume per unit volume will be equal to the volume charge density there. Like if we have a differential volume, let's suppose we have a differential volume that is enclosed by the closed surface. So the total flux that is leaving this closed surface per unit volume will be equal to the volume charge density here. I am repeating it again. The Maxwell's first equation actually states that the total flux that is leaving a differential volume, or that is leaving the closed surface which actually encloses this differential volume per unit volume, will be equal to the volume charge density here. मतलब जितना फ्लक्स इसी क्लोज्ड सरफेस से पास हो रहा है जो इसी डिफरेंशियल वॉल्यूम को एनक्लोज कर रहा है, वो बराबर होगा यहाँ पे जितनी वॉल्यूम चार्ज डेंसिटी होगी. So the divergence of D will be equal to rho v, and actually the divergence of D can be defined as D dot ds divided by del v, as del v shrinks to 0. So this term actually represents the flux that is leaving the closed surface, the flux that is leaving the differential volume per unit volume as the volume shrinks to 0. So this is actually the left hand side, and this left hand side will be equal to the volume charge density there, the volume charge density there. So this is actually the Maxwell's first equation. Remember that the Maxwell's first equation is also called the point form of Gauss's law. Maxwell's first equation को हम point form of Gauss's law भी कहते हैं. This equation is actually called the point form of Gauss's law, or this equation is also called the differential form of Gauss's law. So the Maxwell's first equation is actually called the point form or the differential equation form of Gauss's law. So we can say that Gauss's law is actually called the integral form of Maxwell's first equation. Gauss's law is actually called the integral form of Maxwell's first equation. So this is the first of Maxwell's four equations as they apply to electrostatics and steady magnetic fields, and it states that the electric flux per unit volume leaving a vanishingly small volume unit is exactly equal to the volume charge density here, which I already explained. This equation is aptly called the point form of Gauss's law, because I already told you that Gauss's law actually relates the flux with the charge enclosed, the flux that is leaving a closed surface to the charge enclosed by the closed surface. The Gauss's law relates the flux to the charge enclosed. The Maxwell's first equation makes an identical statement on a per unit volume basis. So the Maxwell's first equation actually relates the charge or the flux per unit volume to the volume charge density, because the Maxwell's first equation makes per unit volume basis. So if it makes the per unit volume basis, so it will relate the flux per unit volume to the volume charge density. So Maxwell's first equation is also described as the differential equation form of Gauss's law, because divergence may be expressed as the sum of three partial derivatives. If divergence is expressed as the sum of three partial derivatives, so the Maxwell's first equation is also described as the differential equation form of Gauss's law, and conversely Gauss's law is recognized as the integral form of Maxwell's first equation. So remember that Maxwell's first equation is called the point form or differential equation form of Gauss's law. Similarly or conversely, Gauss's law is recognized as the integral form of Maxwell's first equation. Now how can we explain the Maxwell's first equation or the divergence? By taking an example. So let's take an example. Let's suppose we have a point charge that is placed at the origin of a spherical coordinate system. So if we have a point charge that is placed or that is located at the origin of a spherical coordinate system, it will have its own electric field. So it will have the electric field intensity and the electric flux density in its region. So let's suppose we have a point charge that is placed or that is located at the origin of a spherical coordinate system. Let's suppose we have a point charge of q coulombs at the origin of a spherical coordinate system. At point P, where this point P lies in the region of its electric field, the electric flux density D will be equal to Q divided by 4 pi r square into AR, if R is the distance between this point P and the point charge. This is actually the electric flux density D at point P, which is at a distance r from the point charge. So we have the point charge that is located at the origin. There is no other charge in its region. We only have this point charge that is located at the origin of a spherical coordinate system, and the electric flux density at point P due to this point charge will be equal to Q divided by 4 pi r square. As we have taken the spherical coordinate system, and we know that the divergence of electric flux density D in spherical coordinate system is represented by the divergence of an electric flux density D in spherical coordinate system is represented by this equation. So we have dr, d theta and d phi. As we know that this electric flux density has the radial component only. There is no theta component and there is no phi component. So if we put this equation, if we put this value in the divergence of the electric flux density D, so in case of R, we will replace dr by Q divided by 4 pi r square. This term is 0, this term is 0 because we don't have any d theta and d phi component. So if this term is 0, so it will result in 0. So the divergence of d will be equal to 1 divided by r square partial by partial r of r square into dr, because these two terms are 0. Here we only have the radial component, so the partial derivative has been replaced by the full derivative because we only have the radial component. So it will be equal to 1 divided by r square d by dr of r square, and we know that dr is equal to q divided by 4 pi r square. This r square will be cancelled out with r square and the result is actually 0. So the divergence of the electric flux density results in 0 if r is not equal to 0. Why the divergence of the electric flux density d is 0? Because the volume charge density here is 0, because we only have the point charge that is located at the origin. There are no other charges. If there are no other charges over the volume, so the volume charge density rho v will be equal to 0. So that is why, according to Maxwell's first equation, divergence of d is equal to rho v. So if divergence of d is equal to 0, it means that the volume charge density will be 0 all over the region except at the origin, because at the origin we only have the point charge. तो इसलिए जो डाइवर्जेंस ऑफ द इलेक्ट्रिक फ्लक्स डेंसिटी है वो 0 आ रही है. क्यों? क्योंकि जो वॉल्यूम चार्ज डेंसिटी है, चार्ज पर यूनिट वॉल्यूम है, वो 0 है all over the region except at the origin, which is infinite. Except at the origin, because at the origin we have placed a point charge. So this was all about the Maxwell's first equation. Thus the volume charge density is 0 everywhere except at the origin where it is infinite, because this divergence of the electric flux density d is equal to 0 if r is not equal to 0. If r is not equal to 0, so this divergence of d will be equal to 0. The divergence operation is not limited to electric flux density. I have already explained this, that the divergence operation is not limited to electric flux density. It can be applied to any vector field. Like we had taken the general vector field A and we had defined the divergence of A. So the divergence can be applied to any vector field. Thank you.